We are now going to continue our discussion of electromagnetic induction with this final video on the unit on electromagnetism. And specifically, we're going to look at now how to determine the magnitude of an induced current, either through using Faraday's law, or for a more specific application, what is known as motional EMF. So let's just have a brief reminder of what electromagnetic induction is once again. When we have a changing magnetic flux through a loop or a coil of wire. So when the amount of magnetic field or the area of that loop or its arrangement with it somehow changes, a non-localized induced voltage, in other words, a voltage that emerges at all points in the wire, an electric field that's emerging in the wire, will produce an induced current. It will drive charges around the wire. And we already learned previously how we can determine the direction of that induced current using Lenz's law, remembering the nature abhors a change in flux, so that whenever we change the magnetic flux, the induced current generates its own magnetic field that will counteract that change in flux. But how do we figure out the magnitude? And that is through something known as Faraday's law. Named for Michael Faraday, the British scientist who discovered the phenomenon underlying electromagnetic induction, Faraday's law tells us how to determine the magnitude of that induced voltage, and by proxy allows us to determine the magnitude of the induced current. Ultimately, what this comes down to is that the induced voltage in this conductor is equal to the rate of change of the magnetic flux. Therefore, the induced voltage in volts we abbreviate with epsilon, and remember we saw that a lot in the circuits unit when we were talking about electromotive force and internal resistance. Epsilon really is ultimately the same thing as delta V, will be equal to delta phi b over delta t, where delta phi b is the change in magnetic flux in Webers, and delta t is the change in time in seconds. Now, a couple things we want to add here. This is actually the induced voltage in a single loop of wire, but if we have multiple loops of wire, we need to multiply by some constant n, where n is the number of loops. So 2 loops would be 2, 3 loops would be 3, etc. Now if you look at your equation sheet, you'll notice there is a minus sign in front of this equation, and what that really is just a result of Lenz's law. That is their way of telling you that ultimately this change in magnetic flux will produce a current with magnetic fields that oppose this change in flux. So we can really just disregard that whenever we're doing calculations, and instead we can really just put the whole thing in absolute value bars. And that will give us the magnitude of this voltage, and then we just use Lenz's law to figure out which direction the current will ultimately go. But this is a voltage, not a current, so how do we get a current from it? Well, we just use Ohm's law as I is equal to delta V over R, where our delta V in this particular case will be epsilon, the induced voltage. So let's go through an example just to see how this works. Let's say we have a 10-loop coil of wire that's in a square shape, as we see here, and every side of the square is 10 centimeters long, and the whole thing has a total resistance of 0.2 ohms. There's a magnetic field going through the coil, and it's directed into your screen, and it gets decreased from 2 Tesla to 0.5 Tesla in 0.1 seconds. So whatever's controlling the magnetic field, we just turn it down this amount in 0.1 seconds. And when this happens, we're going to have a changing magnetic flux. So we want to determine the magnitude and direction of the induced current in this coil. All right, so let's go this one piece at a time. So first we need to do the magnitude, and for that we're going to use Faraday's law, which I've rewritten here. Notice about the minus sign with the absolute value bars. And I'm going to go ahead and notice, though, that delta phi b, in other words, the change in magnetic flux, well, what is the magnetic flux? So the magnetic flux was Ba cosine theta. Now these are arranged perpendicularly here, so in this case cosine theta will just be 1. So we just have the delta Ba, where we have the change in magnetic field and the change in area. Well, the area doesn't change, but the magnetic field does. So taking this a step further, I'm going to have 10 loops for the loops of coil. I'm going to have the change in the magnetic field, which was 0.5 minus 2, final minus initial. The area was 0.1 meters times 0.1 meters because it's 10 centimeters long on each side, and we want that in meters squared. And the time is 0.1 seconds. I stick that in my calculator, and with the absolute value bars, I get an induced voltage of 1.5 volts. Now, to find the induced current, I just use Ohm's law. So I have 1.5 volts over 0.2 ohms, the resistance, and I get an induced current of 7.5 amps. And now that we have the magnitude of the current, we just need to figure out its direction by using Lenz's law. So let's go through that process again, remembering the different steps. First, we need to identify the direction of this initial magnetic field, and that is into the screen, into the page. And now we need to recognize the change in magnetic flux. Is it increasing or decreasing? It is in fact decreasing because the magnetic field is being turned down. And since it is decreasing, that means to counteract, to oppose this change, we need to reverse that. We need to increase the magnetic field going into the screen. So that's what I want to do. So I'm going to, if you notice here, I've just drawn these now, that at all these points, the magnetic field needs to be going into the screen, specifically inside the loop. And now I use my right-hand rule. So if I look at the, let's say, the left-hand side here, well, I want my fingers to go into the screen inside the loop. So that means my thumb will be directed upward. If I look at the top, I want my fingers to go into the screen inside the loop. That means my thumb is directed to the right. So at the right side, if it's going into the screen, my thumb is directed down. And at the bottom, if I want my fingers to go into the screen, my thumb is directed to the left. So overall, when we draw this, we see that the current is going in this direction, or it is clockwise. So the current will be 7.5 amps in the clockwise direction. Alright, this is a slightly different situation. We now have a circular loop of wire with an area of 0.2 meters squared and a total resistance of 16 ohms. And the loop is placed in a 3 Tesla magnetic field that is directed, we see, to the right. And we are going to say that the loop is rotated so that it completes one rotation in 0.01 seconds. And we want to determine the magnitude and direction of the induced current in the loop at this particular moment in time. The reason why I say that this particular moment in time is because as it's rotating, that current will flip directions back and forth. So we want to look at this exact moment. And notice that we have drawn here that the loop is rotating in such a way that its left side is coming out of the screen and its right side is going into the screen. Alright, so let's go through this again. So let's go ahead and start once again with the magnitude. And if I do the magnitude, I'm going to have Faraday's law once again. And alright, this is the part that's tricky. How can we figure out the change in magnetic flux? Because it seems to be changing all the time. Well, let's go from when this ring is at this location to when it rotates 1/4 times. Because when it rotates 1/4 times, it will be at a point of maximum flux. All of the arrows, all the magnetic field lines will be going through it, whereas currently, it's actually at minimum flux. All the arrows are going by it, so we would be going from 0 Tesla to 3 Tesla through the loop. So that's going to be 0, 3 minus 0 for that change in B. My area we were given, it's only one loop. Now this is the part we really want to be careful of. We just said that this change in flux occurred for a 1/4 rotation, but that means if one full rotation takes 0.01 seconds, we need this to be 1/4 the rotation time, which would just be 0.0025 seconds. We calculate that out, and we get a induced voltage of 240 volts through this loop. And just using Ohm's law, we can then figure out that the induced current is simply 15 amps. Okay. Let's use Lenz's law to figure out the direction. So if I'm looking at this, the magnetic field is directed to the right. If we rotate it from this instant, it's going to be increasing for sure because currently we have 0 flux, so it's going to be going up. So we're going to have it increase. So we want it to reverse that change. We want to decrease it or increase it to the left to counteract this increase to the right. So when this starts to turn, I want all of my loop, when I have it go this way, I want the magnetic field lines generated by the induced current to go to the left through the loop when it makes it through that 1/4 rotation. And if that's the case, I can now use my right-hand rule and say, okay, I want my fingers going into the board at all the different places around, and I see that, in fact, this will be going in the clockwise direction once again. So the current is 15 amps in the clockwise direction. Now let's look at a slightly new situation, because in both of those, the loop of wire may have been rotated, but it was pretty much staying in the same position. We were just altering the amount of magnetic field that went through it. But now let's look at a new situation where I have this loop of wire with, we're going to say that, this side is 4 centimeters, this side is 8 centimeters. Its total resistance is 2 ohms. It's in a 5 Tesla magnetic field directed into the screen, and it's going to be pulled to the right at a speed of 2 meters per second. Now, if it was being pulled through the magnetic field and was not leaving it, well, then the magnetic field through it would be constant, the magnetic flux would be constant, and there would be no induced current. But as soon as we start to pull it out of the field, well, now the loop is leaving the field, the amount of magnetic flux going through it is going to decrease, and that's going to, of course, induce a current in the wire. But how exactly do we go about solving this? Because if we look at Faraday's law, well, how do I figure out this delta B over A? Now, you could figure out the change in area here, because we could say, oh, well, it's being pulled at this V, and that's going to make the part of the area that has a magnetic field in it decrease. And this is actually the right idea here, because now, if I look at this, I've got delta B times A for the change in flux, so I'm really going to be changing the area. But what is this area always going to be equal to? Well, it's going to be equal to this side L times whatever part of this side over here that is still in the field, which we're going to go ahead and label as delta X, and then over delta T. But something we can notice is that delta X over delta T is the same thing as velocity. And so therefore I end up with this more simplified equation that epsilon is equal to BLV. And this is a specific situation of something that's known as a motional emf. In other words, an induced voltage that comes from the motion of the loop entering or exiting this magnetic field. So it results really from a very, very specific situation, but it's very useful for that specific situation. So we have epsilon is equal to BLV, where epsilon is the induced voltage in volts, B is the magnetic field strength in teslas, V is the velocity of the wire being pulled through in meters per second, and this is crucial. L is specifically the length of wire arranged perpendicular to the movement through the magnetic field. So another way to think about that, it's the length that is being pulled across the magnetic field lines as it's entering or exiting this field. So going back to this particular situation, I've gone ahead and erased a couple things here, but as this is pulled outward, this side and this side are not going to be crossing the magnetic field lines, but this one is. It's going to be crossing all of these here. So this is L. It is arranged perpendicular to its motion. So now that I have BLV, I'm going to stick in some values. I'm going to get 5 Tesla times, 4 centimeters is 0.04 meters. The velocity is 2. And we get a total induced voltage of 0.4 volts. And now that we know the resistance, I can just do that Ohm's law and find that the induced current is 0.2 amps. Now let's figure out the direction of this induced current. Once again, using Lenz's law, the magnetic field through the loop is into the screen. It's decreasing, the flux is, because we are leaving the field. So to counteract that, to oppose that change, the magnetic fields generated must go into the screen inside of the loop. And if they're going into the screen inside the loop, I can use my right hand to say, okay, I always want my fingers to go into the screen. So at the top, if they're going into the screen, it's going to be going to the right. On the right-hand side, if it's going into the screen, it's going to be going down. On the bottom, into the screen, it's going to be going to the left. And on the left-hand side, if it's going into the screen, it's going to be going up. So once again, we've gotten that the current is 0.2 amps clockwise. But ultimately, why is this all so important? Why is electromagnetic induction such a useful tool? Well, thinking about it, we've ultimately either moved a coil of wire in a magnetic field or moved a magnet with respect to a coil of wire and generated from that a current. And what we are doing is we are obtaining electrical energy from movement energy. Or in other words, we are transforming mechanical work into electrical energy. And this is actually the basis for electric generators. How we get the vast majority of electricity in pretty much every place in the world. Now, this is essentially the reverse of an electric motor. An electric motor took electric energy and converted it to mechanical work. We're now going backwards. We're taking something that's moving and from it deriving a current. Now, an electric generator, a real big turbo generator, looks something like this. You can kind of see that, this is a person's scale would be about that. So these are humongous devices. And inside of these, you have turbines, and these turbines are driven through various mechanisms. They can be driven by the wind. They can be driven by water. They can be driven by steam. But ultimately, whatever it is causes them to move, causes coils of wire to move in a magnetic field, or magnets to move inside coils of wire, depending on the exact turbo generator, and from there, current is produced. And this is how we harness different forms of energy and produce electricity. And lastly, as I said, this is pretty much applicable to every sort of energy production. Fossil fuels, nuclear power, wind power, hydropower, geothermal power. In fact, the only one that does not produce electricity in quite this way is solar energy, and we'll get more on that later in the year. So what are our key takeaways for this final video on electromagnetism, specifically talking about electromagnetic induction with Faraday's law and motional EMF? Well, can we determine the magnitude of an induced voltage and by proxy an induced current by using Ohm's law, using Faraday's law? Knowing that epsilon, that induced voltage, is equal to the number of loops times the change in magnetic flux. That's either the change in magnetic field or the change in area over the change in time. And additionally, can we determine the magnitude of a motional EMF using epsilon equals BLV? Keeping in mind that these is really just used for specific situations when that loop is being pulled into or out of a magnetic field.